Let's see what we can do with a converging mirror. This is the sort of mirror that you would use for shaving or for putting on makeup. If you get very close to it, then you see a right side up image of yourself and it's magnified. But then as you back away, you see an upside down image of yourself in the mirror. We can try with some ray tracing to understand why that happens. And the upside down image of you is reduced in size. Let's take another example of a converging mirror. This is basically just a bigger version of that mirror that you saw a moment ago. And here is a single green light bulb. And it's an old incandescent light bulb. So if you look really closely, you can see the filament. What we're going to see, and we'll work out the ray tracing and the equations to back this up. What you're going to see is an inverted, so it's upside down. You'll see an inverted real image, a vividly real image, pretty convincingly real, of this green light bulb will appear down here. So when I turn this so that you can see it, you will imagine that you see a second light bulb down here, upside down. Let's see how that works out. This is a real image because if I put my hand where you think the image is, it indeed blocks the rays. It really creates a very vivid optical illusion that there's a second light bulb there, even though there is only one bulb. And let me show you just the mirror. And the mirror alone that we use to do that looks like, see, here you are upside down and demagnified. And now here you are right side up and magnified. So that turned out to be with the object 2 focal lengths away from the converging mirror. So I think what we can see if we moved the object, the real light bulb, a little closer, if we moved it to the focal length, then you would see the image blow up, magnification would sort of diverge. If we put it at 1.5 focal lengths, you'll see a different magnification. So let's try that. So I'm going to slide the bulb that way, and I'll do it while you're able to look. Actually, might be easier to move the mirror. So here they're 2 focal lengths apart. 2 focal lengths, the magnification is -1. So it's an upside down image, same size as the original. And as I move the mirror and the object closer together, you see the image gets bigger and bigger. It remains upside down, but it gets bigger and bigger. And then, I think once I reach the point where they're only 1 focal length apart, the image sort of blows up in size. And now you see a right side up virtual image. And I guess you can see that it's a virtual image. Okay, now let's try a diverging mirror. This is a mirror that curves out like that. This is a sort of mirror that's used as the side view mirror in a car so that you can see wider angles and see what's behind you. It's also sometimes used by a shopkeeper to observe what's going on in the aisles of a store. But what you can see here is that the image is never upside down. It's always right side up. And it's also always smaller than the original. So you'll see a reduced and right side up image. And we can work out both the ray tracing and the math. And it will also turn out that the image is virtual because you think you see something behind the mirror, but really there's nothing back there. So it bows out like that. Yeah, so here the rays going into the mirror are all parallel, but you can see them come out in diverging directions. So that's a diverging mirror. Yeah, so the rays going in are all parallel. So in contrast with the converging mirror, you can see that the rays emerge and focus to, the parallel rays emerge and focus to a point. Those are the parallel rays that go in, and they reflect off, and they converge to a point. Soup spoon, this side you see your right side up, reduced image of yourself. This side you see an upside down reduced image of yourself. And then this soup spoon, I think, doesn't have quite the right radius of curvature to be able to do this, but then I think with a better soup spoon, if you get it really close to your eye, then suddenly you see a right side up magnified version of your eye. Using Snell's law of refraction, we know that index 1 sine theta 1 equals index 2 sine theta 2 if the incident angle is 0, meaning perpendicular to the surface. Then the outgoing angle, the transmitted angle is 0. We can see, here, let's see. So here's a beam of light coming up from the underneath side of a surface of water. And if it hits the water surface perpendicular, then it doesn't change direction. Now we can gradually change the angle at which the upgoing ray meets the surface, the water-air surface. So we've got water down below, air up above. And we can make the angle bigger and bigger. And note that the index of refraction of water is about 4/3 the index of refraction of air. So here we go. So we're up to about so you can see as I increase the angle of incidence, the angle of refraction gets bigger faster and faster. And this is, in the way Richard Muller describes this, is he says the ray always bends toward the slower medium. So you have the ray in the faster medium in the air bending toward the surface of the slower medium, the water. And we can go, and actually this is nice because you can see the incident ray on the right, and you can see the reflected ray on the left down below, and then you can see the refracted ray on the left up above. And then we can continue to make the angle of incidence bigger. And eventually we'll reach a point where the angle of refraction reaches 90 degrees and then can't go farther than that. That's basically the statement that the sine of the outgoing angle can't get bigger than 1. And then after that you have what's known as total internal reflection. So let's see. So we're going to make this incident angle bigger and bigger. Now all of a sudden everything is reflected. There is no refracted ray. It's completely reflected. So this only works when you're starting out inside the slow medium. So if you're starting out inside the slow medium, you can get trapped inside the slow medium. So if you try to hit it with just a grazing angle, everything is reflected. There's no refraction at all. This turns out to be a really excellent way to make a mirror if you can arrange to have the light bounce at a grazing angle, then it all stays inside. And I think what appears to be something escaping is really just you're seeing a little bit of light travel along the plastic surface that's holding the water into the tank. Okay, so now you see we get a refracted ray again. Okay, let's try the other direction. So we can start in the air. Start in the air, we can go straight down, or we can gradually increase the angle of incidence. And you see that the angle of refraction is smaller than the angle of incidence because the water is more dense. So again, the ray bends toward the slow medium. In this case, that means it's bending kind of toward the water. The water is a slower medium. And we can make the angle bigger and bigger. And you see that effectively the ray is bending toward the water. There's some extra reflections I think we see from the laser light bouncing off of the plastic. Okay, but basically this is just like a time reversed version of what we saw for the ray starting out below the water surface. Here's another pretty good trick. A glass prism actually makes a terrific mirror. In fact, I think that's a trick used to get a good mirror inside a lot of cameras. So if I put the laser beam into the prism at this angle, fine, you see the refracted ray. You see the rays go from the glass air to the glass to the air. If I go at an angle such that when I meet this surface, I'm past the total internal reflection threshold, then there is, you see now there's no, up here you see the refracted ray, but if I go at an angle like this, then there's no refracted ray. Everything, 100% is reflected due to total internal reflection. And so then I get a really nice mirror effect, 90-degree mirror effect there. Oh, let me try this with the lights out too. I'm coming in, there's air to glass to air. Air to glass to air. Fine. But then if I go down here, then there is no longer any refracted ray. Nothing escapes the glass over here on the top left. So I get perfect reflection at 90 degrees. No refracted ray. So this makes a very nice This piece of glass at that angle makes a very nice mirror, even though there's nothing dark behind it. So you see, you can see my hand, which is actually on the bottom of the prism, but you see a pretty nice reflection of my hand. So when you look here, you see my hand, which is actually coming through this 90-degree mirror effect. So thanks to total internal reflection, this block of glass shows you a nice mirror, a nice reflected image of my hand down below. So there's total internal reflection. So another pretty good example of total internal reflection is, I think you can see, oh yeah, you think you can see that the light gets trapped inside the glass, bounces back and forth. I think I can make, so if I make the angle even bigger, it's even more obvious. So you see the light is trapped inside the glass because at that angle we have total internal reflection. Whereas and then I can even do that with a curved piece of glass. Oh, that's pretty good. Oh, look at that. So here you can see the laser light trapped inside the glass by total internal reflection. And you can even make light bend around a turn that way. Yeah, so here's some optical fibers. You can see I put light in one end and then through total internal reflection it comes out the other end, even though it's curving around. Okay, let's try this little system called blackboard optics. We're going to take some parallel rays from the lasers and we're going to pass them through a number of different optical surfaces and see what happens. What we're starting with is a flat two-dimensional version of the converging mirror. So here's a little surface. It's going to go like this, so it should focus parallel rays as they get reflected. And then we can just flip it over, and it's shining on the other side too. So this will be a diverging mirror. So let's zoom in and turn out the lights and see what that looks like. So that's pretty good. So you can see the parallel rays coming in from the left, and then you can see that the rays converge to a point right around here. Somewhere, whoops, well, okay. They converge to a point that's about this distance out. Actually, I think you can also see there's a ray up there, and here's a ray along the axis, and here's a ray down here. So you can see they all find, if I really keep the laser beam parallel, horizontal, then you can see they focus here. And so you can see the red laser is a little dimmer, but I think you can see that they all converge here, and I might even be able to do that with chalk. Yeah, so I think you see all the rays converge to this point here when they reflect in the converging mirror. Okay, now if we turn the mirror around, it becomes a diverging mirror. It's pretty faint on the board. Well, if I take the green laser, here we are right on axis, up above, even higher, down below. So you can see that parallel rays coming in diverge instead of converging. And then they actually appear as if they came from a focal point behind the mirror. If you were to extend the reflected rays back to the right side of the mirror, then they would appear to emanate from a focus back behind the mirror. Well, that's pretty good. So there, I think you can see, well, that's even better. Yeah, I think you can see the diverging rays there. And if I flip it around, I think you definitely see the converging rays. And this way, you see the diverging reflected rays. Okay, now we have a piece of glass that looks like this. So it's thicker in the middle, thinner on the ends. So this will be, actually it doesn't matter whether you make it like this or like this. So this will be a focusing lens. So we'll see parallel rays coming in from the left get converge to a focus, and you're going to see the focus right around here when we turn the lights down. So I think that's pretty good. So you can kind of see, you can see the rays coming in and focusing to a point over here. And then I think I can make it a little more obvious even with the green laser. I think then you can also see, if I put two similar lenses right next to each other, I could do that this way. So you can see now the focal length is smaller. They converge sooner. I could put them back to back in two different ways. I could also put them back to back this way. Yeah, and you see now that there is, it cut the focal length about in half. So this is like you can wear two pairs of reading glasses, one on top of the other, and you get double the focusing power. Okay, so here's just one, and then you put them two next to each other, and basically cut the focal length in half. So that's pretty good. you can see that this lens has a shorter focal length than this lens. So here we're bringing things to a focus right around here. So instead of way out here, the focus is in here. So it looks like about a factor of 2 or 3 smaller focal length. And then you can see here if you can instead use a diverging lens instead of a converging lens. So it's a defocusing lens instead of a focusing lens. And you see parallel rays coming in on the left turn into diverging rays instead of converging rays on the right. And it turns out if you are nearsighted, you actually wear diverging lenses, and if you're farsighted, then you wear converging lenses for corrective vision. Yeah, so parallel rays coming in on the left turn into diverging rays on the right with the defocusing lens. Now we're back with the thick converging lens, and I have two lasers whose rays spread apart as if they're coming from a common point here. I think you can see the two rays focus to a point on the right side, and if we are 2f away on the left, then we get a focus 2f away on the right. And then if we're a little farther than 2f on the left, then we wind up closer than 2f on the right. And if we get closer, then they get farther away on the right. And if we actually eventually reached a distance of f on the left, then they would become parallel on the right. So they would not converge until infinity. So if you have 2f on the left, you get 2f on the right. You have more than 2f on the left, you get less than 2f on the right. Less than 2f on the left, you get more than 2f on the right. And if you get to f on the left, then you get infinity on the right, so the rays come out parallel. So this looks like the focal length on the left, where you see the rays come out parallel on the right. And then if they look about equal, it's 2f on the left and 2f on the right. Yeah, and then here's less than 2f on the left, more than 2f on the right. And here we have more than 2f on the left, less than 2f on the right. Okay, so I can take my parallel beams of laser light and figure out what the focal length of this lens is. And it looks as if the rays come to a focus at about that distance from the lens. It looks like it's a little over 40 centimeters. If I place some kind of an interesting object 80 centimeters away, so that's 2 focal lengths. So let me take some kind of an interesting object, like a green and red light bulb. Here's green on top, red on the bottom. And let me go 2 focal lengths away. Okay, that's pretty close. So now you want to say, where is it going to appear on the other end? And I claim that if it's about 2 focal lengths away on the left, then the image will appear about 2 focal lengths away on the right. Let's see where that happens. So it's not there. Seems to be... Oh, look at that. You can see a pretty good image. You can actually see, it's actually a clear enough image that you can see the filaments. Yeah, so that's a pretty nice image. You can actually see the filaments of the light bulbs. So that's in focus. And it looks like, in this case, the distance is the same on either side. So that happens when you have 2 focal lengths on the left, 2 focal lengths on the right. Now, if I get a little farther away on the left, then to stay in focus, I have to get closer on the right. Okay, now I'm back in focus on the right. So you see I'm more than 2f away on the left, and I'm closer than 2f on the right. You see a nice clear image of the filaments. And then I can even try to get a little farther on the left. And then the image should be even closer on the right. And notice, by the way, in all of these cases, in real life we have green on top, red on the bottom, but in the image we have red on top, green on the bottom. To my eye, that's a nice sharp image of the filaments. We're considerably more than 2F on the left, considerably less than 2F on the right. And if I get really, really far away, if I get as far away as I possibly can, then I'll be just a little bit beyond F on the right. Let's see if we can do that. Okay. Oh, notice the image is getting smaller and smaller. So there's a nice sharp image of the filament on the right, but the camera is not properly focusing on it. So I think this should be about 40 centimeters away from the lens, because now that we're much farther than 2F away over there, looks like maybe 50-ish centimeters. I could even try to get a little farther away over here. I'll move in until it focuses. It's getting smaller and smaller, but the distance is slowly approaching that 40 centimeter focal length. Oh, see, that's pretty good. You can see it's in focus. You can see it's a nice sharp image of the green filament. And I see with my eye a nice sharp image of the red filament as well. And the bulbs are way back there. So, you know, if I wanted to do the opposite, suppose I want to make like a homemade movie projector. In that case, I want a big image on the far wall. So to do that, I have to put the lens close to the camera, just a little bit more than one focal length away. And if I do that, then I should get a nice big image on the wall pretty far away. Yeah, actually, well, that's pretty impressive. You only see the image is so big, you only see the green, you don't see the red. But I think if I put it on the wall, you can see both the green and the red. Okay, so now I have the lens just a little more than a focal length away from the object over here on the left. So they are, well, I guess they're between 40 and 50 centimeters apart. So I guess they're like about 1.2 F or something apart. And then I can look and see where the image appears. And it's actually a nice sharp image over here on the wall. And you can see it's big. Green's on the bottom, red's on the top. They're both clearly in focus. And I guess you can't see what I'm doing, but you'll watch if I move the lens back and forth a little bit, it goes out of focus, it goes out of focus. So I have to pick just the right distance to get a nice sharp image of the two filaments. And you can see with the math that that distance is just the right distance, so that 1 over F equals 1 over D object plus 1 over D image, where F is the focal length of the lens. So you want to make a movie projector where the image is big and far away from the projector. To do that, you put the film just a little more than a focal length away from the lens. Okay, and from this perspective over here, so you can see the light bulbs and the lens and the image all at once. Here's my green light bulb, here's my red light bulb, here's my lens. And you can see if I move the lens that way, the image of the filaments goes out of focus. I move that way, it's out of focus, but at just the right distance, then the image of the filaments is nicely in focus. Okay, let's measure the wavelength of light. And we're going to do it for red light and green light. We have a red laser and a green laser. We have both the red and the green lasers shining light through this diffraction grating. So it's a couple of slits, and the two slits are 1/4 of a millimeter apart, 0.250 millimeters apart. And the prism is because the two lasers are stacked on top of one another, and you want to bring one laser beam down close to the other. So you can see that one laser is probably about 5 or 7 centimeters above the other. And you can see by the time you get down to the grating, thanks to the prism, the red spots and the green spots are actually just a few millimeters apart, maybe less than a centimeter apart. Okay, so that's what the prism is there for. We have the lasers over here, and then all the way across the room we have a screen, and on the screen you can see the red spots and the green spots, and you can see them better with the lights out. But before we turn the lights out, let's look and notice how far apart everything is. So if I pull this tape measure taut, is attached right next to the diffraction gratings, then I measure about 9.16 meters. So from the diffraction grating, where the slits are, to the screen is about 9.16 meters. The slits are 0.250 millimeters apart. You can see the slits on the screen. There are the green slits, and there are the red slits. And maybe you can tell that the red slits are spaced a little farther apart than the green slits. But anyway, what I did is I measured from dark spot to dark spot to dark spot to dark spot, and I got a tape measure out, and I measured, okay, it looks like I can probably count about 6 red dark spots. Let's see, 1, 2, 3, 4, 5, 6. I decided I could get a pretty good measurement of 6 spot widths. So yeah, 1, 2, 3, 4, 5, 6 spot widths of red. And I decided I could get a pretty good measurement of, I think, 13 spot widths of green. Then what I wrote down on the board, then, for the red case, I measured 6 spots were 14 centimeters, so that's 23.3 millimeters per spot. For the green spots, I measured 27 centimeters for 13 spots, so that's 20.8 millimeters per spot. So you can see the green spots are narrower than the red spots once you count a bunch of them. Then the wavelength that we infer is the slit distance, little d, times the spot distance, big D, divided by the distance from the slits to the screen, which is big L. So big L is 9.16 meters. Little d is 1/4 of a millimeter. And then big D is what we measured by counting spots. So for the red case, I got 23.3 millimeters. So you take 0.250 millimeters times 23.3 millimeters divided by 9.16 meters, and that gave me 636 nanometers, or 0.636 micrometers, which I think is pretty good. I think for a helium neon laser, in real life, the established answer is 630 nanometers, so I probably did a little better than we deserved to there with our imprecision counting spots. And then for the green case, 0.250 millimeters for the slit separation times 20.8 millimeters for the green spot separation, edge to edge, and then divided by, again, the distance, 9.16 meters from the slits to the screen, and I got 0.568 micrometers, which is 568, so you say 570 nanometers. And for the green, 543 is the established answer for green, and I think 630 is the established answer for red. That was pretty good, actually. Yeah, so it's 543 if measured really carefully, and just counting those 13 spots and measuring with a tape measure, we got 570 nanometers. So anyway, this is how you can measure the wavelength of light. You can use the interference pattern when you run monochromatic light through a pair of slits of precisely known separation.